am Abhinav here, and I will be walking through the code of a solution of a Kaggle problem called the Statefarm Distracted Driver Detection, which is about the driver to creating a computer vision based machine learning model which will identify that whether the driver is getting distracted in predicting the driver's activity on the basis of the input image and predicting the driver activity in one of the 10 classes. So this is the link of it. So this is you can just browse here the Statefarm Distracted Driver Detection, and the Kaggle problem will come. So as we can see that we have the data folder, and we can get the data from here. So the classes are C0 safe driving, texting, C1 means that texting right, C2 and so on. So there are in all 10 classes. So what we have to do is that we have to identify and to make a machine learning model that if we input an image into it, we will get the prediction as the correct prediction that what the driver is actually doing, and we can set a alarm or create a product in which the driver distracted activity can be identified. So in this we have a data folder, we have all the images and the driver list and the sample submissions. So we'll be in this, so I have downloaded all this, and inside my distracted driver this folder in which I have some of those images, test and train, or as you can see here. So I'll be walking you through the code of it. So let's start with that how I approached this problem. So in the first stage what we will be doing is that we will be importing all the libraries and that we are having. So it is just we are importing some of the pandas and the Seaborn SNS is for the plotting, and the Keras layer for the convolution neural networks. So the approach that we are going to follow is that we are going to use a stacked CNN architecture with various layers of CNN, which we will be making it from scratch, and then we'll be training it after pre-processing those images, and we will be inputting it, and all the layers of the CNN will be trained, which will further identify the features from the input text and will result in a proper classification model for classifying the image, which will classify it into the one of the 10 classes. So first of all, we have just imported the libraries. I will be walking you through the code, and then I will be showing you the demo that how it actually works, and that how we can predict it from a given image or from a from a running video itself. So on the first we'll be just creating the CSV for generating some CSV files, and the pickle dir is for generating some pickle files that will be trained, and this is the model path where all the models will be saved, and this is the train dir and the test dir. This is the files for the training files and the testing files. Next I'll be just having a CSV file which I'll be creating for the train and the test CSV, which will just store just the this one, the location of it, and we will be just storing the file path of them and the class name. So it will help us in later on when we'll be doing the predictions on them. So I just created a CSV which will store the training data paths and the corresponding class for a particular image. So now we are just going to the data analysis, that how much data samples we have for. So we are having, first of all, there is no non-null object, and we can see if I can show it to you here. as you can see, so we are having the data train is having the file name for the corresponding image, and then we have the corresponding class name, and then we are just distributing it, identifying that what are all the samples we have for each corresponding to each class. I have already told you that these all classes means the different have a different meaning corresponding to whether the driver is texting right, left, drinking water, operating the radio, and so on. These are having the same, and we will be identifying the driver's actions on the basis of it. So as we can see that from this value counts that all the classes are having almost the equal number of data samples, that is the data set is perfect, almost balanced, and then we are having we are just finding out for the duplicate, is there any duplicacy, and then further it's just a bar chart to identify that the proper data set for all the classes perfectly balanced here, almost. And likewise for the data test is having again the CSV file, which are having we are having 79,726 test images, and we need to predict our model on it. So we have the observation that we have 22,424 training samples images distributed into the 10 classes, and which roughly translates into 2,424 to approx 2,500 images per class, and we are having 79,726 testing samples. Okay, here it will be testing. So now what we are going to do is that we are going to convert the class labels into the numerical values, that is the ID labels, and the labels to ID. Labels means the labels ID is a dictionary, which will convert the labels into a ID, that is a numerical value, and ID labels means, and we'll be storing it into the pickle file, which will later on use it while we are making a script to predict this model on a particular image. So it will identify that particular class, and then we will be identifying that particular class name from that dictionary. So after it, we are just we have distributed it. We are splitting the training data into training and the test samples, or the validation samples, training and the validation, into the 80-20 ratio. Further, we are just distributing it into the 128. We are some of the images are also now this stage is for the pre-processing the image. So we are getting an image path. What we are doing, we are translating into the square unit size image into the 128 by 128 image vector, and then we'll be flattening it. This code is for the np.expand redems is for the flattening it, and then we are going path to tensor is just it is translating it for all the images in the directory. So np.vstack will do collectively we are getting a complete matrix having each row as the feature vector of that and the matrix, this flattened matrix that's obtained. So here in this code train tensors, we are standardizing the model. We are standardizing all those image vectors. So again, for the validation data for this, we are doing the same for the validation data. Here now we are defining the architecture of the model. So we are, as we can see, that we are adding first of all a convolution layer, then there is a max pooling layer, and then these are the 4 convolution and the max pooling layers stacked one after the another, and there is a dropout use 50%, and then it's a flattening layer after it, and there's one dense layer, and then again a dropout, and then we are having the final softmax layer for the 10 classes that we have already we know that with 10 classes meaning. So this is the summary. After it, we just compile our model using this optimizer RMS prop and the categorical cross entropy, which is in this corresponding for the binary class. We use the binary cross entropy loss function, and this for the loss function for 10 classes. So the multi-class we use the categorical cross entropy, and this is the matrix is the accuracy, which will here we will be creating a checkpoint. It will store those models after every epoch, and it will be saved only when the accuracy obtained is better than the previous one. Okay, so here now we are training it for the 25 epochs. It will take some time, as you can see here. It is going to 846, that is roughly 5 minutes approx. More than 5 minutes, I think. Yeah, 10 minutes, 10-15 minutes per epoch. So all those improvements will be saved in this model folder, which I can show to you here. So all those these are the models which will be stored saved in your directory. And after that we are just drawing a history of it, that whether this we are drawing a plot for the training and the validation loss, training accuracy and the validation accuracy. We must see that whether over the period of time or over the period of the epochs, whether the training loss has decreased and or the training accuracy has increased. So it should be the ideal one. So as we can see, yes, it has almost decreased training loss, and same way for the training accuracy, we are getting improvements over it. Now we are analyzing the model, that how the performance of our model is. We have some matrix for, like, we find the confusion matrix, precision, recall, and the F1 score to analyze the model thus created. So this is all, these are all the code for creating the confusion matrix, and we are just predicting on the validation data. So this is identifying the percentage, that is the 99% of the classes are correctly classified. It's the diagonal. This is the true label, as you can see here. This is the true label, and this is the predicted label. So the 99% of the classes corresponds to C3 are perfectly classified. The 1% probably goes into distributed in some other classes like C1 to C9 except C3, and same way for the C2, and so we are getting class wise accuracy also roughly much better. For the C6 it goes to 100%, almost 100%. So here we are finding out the percentage here. So in the confusion matrix is the 99 denotes the 99% of the C3 samples have been which are truly labeled as C2 are predicted also in the C3 category. If I show you, the C3 is this is the confusion matrix, right? So true and the predicted are 99% correct. And lastly, I'll be finding out the precision and the recall and the F1 score. So we are getting out really exciting values of the accuracy, precision, and the recall, and the F1 score. So F1 score is just the harmonic mean of the precision and the recall, and the accuracy is also another matrix. So so in all, I think that's it for this video. In the next video I'll be showing you the demo of it on a particular image and a particular video also in the next coming video. Okay, thanks for it. Thanks for listening. Bye.